Good afternoon. How are you doing? Everything is fine? Okay. So, I started the video recording of the lecture. I wanted to inform you, but don't be shy. You have to ask questions, no matter if you are recorded or not. Okay, do you have, by the way, any questions so far? I think you should have seen the exam dates on the website. Everything is there. Any information is there. No questions? Perfect. Okay, so today, let me just refer to my website. I'm sorry, I closed it. I am opening now and sharing the screen. 1 second. Good. Okay, here we are, lecture notes for Science of Climate Change and Climate Actions. We talked during the first 2 lectures about climate change in general, a very brief introduction, and we talked about the Earth system. The Earth system, and we emphasized that our purpose is to model their system in order to be able to make predictions. So we need to make predictions of future climate. This is what Science of Climate Change aims to. And in order to make these predictions, we need to first gain an understanding of how the Earth system works, and in particular the relevant processes, and in particular climate. On the basis of this understanding, we need to set up models, and they are mathematical models that allow us to predict the future climate. Of course, what we want to predict is unknown, and the required information is given by the so-called input data. This is what we said, and I think that in order to better understand the science underlying it, we need to say some more about climate models. And in fact, as you see, there is a link here titled Climate Models. But before referring to this link, to the related lecture note, I want to go back to the previous one, because I included into the lecture that we used last time an additional section that is a kind of introduction to the mathematical models that we are interested in, and in particular the climate models. I don't have a presentation for this additional section. I will use the Blackboard to show you some sketches and to illustrate the development of the theory in a very simple way, because we don't want to get into the fine details, but I want to give to you an idea, a clear idea of how the models are structured. Why? Because we need to understand how models work. We need to understand the underlying theory. And what is the purpose of this understanding? It's not just speculation. It's not just curiosity. We need to understand how a model works, because if we apply the model, and this is why we are here, because we want to better know how to apply the models, in order to make the predictions, we don't need just to know what kind of model we should use and run it. We have also to understand, because understanding helps us in getting the uncertainty of the model in getting the limitations of our predictions and the peculiarities. If we understand, we can make the best use of the predictions. And even if we don't develop these predictions, when we get an information about a prediction of future climate, a prediction of a strategy for climate change mitigation and adaptation, in order to fully understand this information, we need to know how the predictions were derived. We need to know the underlying theory, at least in principle, at least part of it. And this is why I want to give to you some additional knowledge about this. First of all, we are talking about mathematical models. And they are models that aim to reproduce with a mathematical scheme the functioning of the Earth system, parts of the Earth system. And you don't have to be concerned by mathematics. Mathematics can be very simple in some cases. And in fact, I will use very simple examples. Indeed, some models have a very simple structure. Some others are more elaborated, more complicated, more detailed. Some of the models reproduce only a part of the climate system. Other models try to reproduce the whole of it. Some models work at the local level and reproduce the climate of a single region. Other models work at the global level and they aim to reproduce the whole of the climate system. Basically, we have to start from the knowledge of the processes that we want to reproduce. What do we want to model? Temperature, rainfall, water resources availability. And basing on our needs, we then identify the best model and we develop the most appropriate model. Keep in mind that in general, these variables we are interested in are varying in space and time. So these models are challenged by a very difficult task to model spatial-temporal variability, spatial and temporal variability. Variability in time means that at a fixed location, you have a variable that is varying during time. Variability in space means that even for fixed time, you have a variable that is varying in space. And these processes are highly varying in space and time. The Earth system processes are characterized by a very, very strong heterogeneity. Heterogeneity means spatial variability, and are characterized by a strong variability in time. So think, for instance, think of temperature. Temperature is not strongly varying in time. Okay, we have a day-to-day variability, but usually temperature is quite smooth. The progress of temperature in time and also in space is quite smooth. So temperature is relatively easy. And this is why we say that temperature predictions, temperature simulations are more reliable than the simulation of, say, rainfall. Rainfall is more variable in time and space. We know during summer, sometimes we get completely wet for a storm that is very local. We move 100 meters and no rain. And these storms usually last for a very short time, like few minutes. The summer storms usually is few minutes. So you see a strong variability of processes that pass from zero, variables that pass from zero to extreme values within a limited space and a limited time. This is a fascinating challenge, but it's also an art challenge. It's quite tough. So how can we select the models then? Okay, we need to know the variables we want to simulate. And these variables are unknowns. And how should the model be structured? The models are, as I said, mathematical models. And they are basically systems of equations, systems of a number of equations. And, you know, no problem. We are used to deal with the systems of equations since the secondary school. It's not really a problem. And we know from the secondary school that to solve a system of equations, we need as many equations as the number of unknowns. At least we need as many equations as the number of unknowns. So when we have identified our unknowns, we know how many equations we need. And our unknowns may be one only, like temperature, but maybe in several locations. And therefore, if we are interested in temperature in 2 locations, we have 2 unknowns. And we have to rely on at least 2 equations. Or we may be interested in 1 single location, but we want to model, besides temperature, rainfall. And this is the second unknown. 2 unknowns, at least 2 equations. Typically, these equations are related to each other, meaning that it is it is very infrequent that we have a single equation incorporating a single unknown. Very often we have that each single equation incorporates a number of unknowns. So we need to solve them together, not separately. As I said, we need at least number of equations that is equal to the number of unknowns, but we may need additional equation. And let me explain why. Because if I want to simulate, for instance, rainfall depends on temperature. Even if I'm not interested in temperature, in order to model rainfall in a very rigorous model, I also have to express rainfall depending on temperatures, even if I'm not interested in temperature itself. This means that I need an additional variable, which is not to be predicted, but it's necessary to describe the state of the system. It's necessary to make the prediction I want to make. I want to make a prediction of rainfall. I also need temperature, because temperature describes the state of the system. If temperature is too low, it's not rainfall, but it's snow. So you understand the difference. Depending on the state of the system, our equations, our prediction changes. These variables that describe the state of the system and are not to be predicted are called state variables. And you see a box here in my lecture notes, state variables. And there is also a link to Wikipedia. They are variables that are used to describe the mathematical state of a dynamical system. Dynamical means evolving in time. And these state variables, therefore, are necessary for prediction. Another example is, for instance, river flow depends on precipitation upstream. Of course, river flow is originated by precipitation somewhere, but it also depends on the water storage upstream. Because if the river can store water, like for instance in an artificial reservoir, you understand that the river flow downstream, the storage changes. So the storage is another state variable that I need to describe. Therefore, we can update our definition by saying that we need as many equations, at least as many equations as the number of unknowns, meaning variables to be predicted, plus the number of necessary state variables. So what kind of equations should we call into play to describe an Earth system process? Earth system processes have something in common. They are they are originated by the energy of the sun. They are originated by energy exchanges. Remember, the Earth system is, most of the processes, almost all of them, are fueled by the energy of the sun. And direct energy, or energy that was stored, accumulated, given by the sun and stored, for instance, in the Earth nucleus. And most of these processes involve flow, transfer of mass. So we may, in more theoretical terms, say that most of these processes are physical processes, which means governed by the laws of physics. Movement of bodies, transfer of mass, and energy exchanges. So, if we get into this context, physics, describing the movement of mass and bodies, describing energy exchanges, what are the most immediate equations that we may use? It is quite obvious, if we have some knowledge of physics, that we think of applying conservation laws. And this is what I want to talk to you about today, at least in the first part of this lecture. What are conservation laws, given that our models are based, can be based on these equations, given that these equations are ideal candidates to describe Earth system processes? What are conservation laws? Intuitively, I think that you know, most of you already know, or at least have heard of conservation of energy, conservation of mass. Conservation laws are also called, for instance, mass balance equation, or continuity equation. The mass balance equation is also called, or conservation of mass is also called continuity equation. So let's try to understand some more. And I want to refer to a simple example. I want to introduce what is a conservation law with a simple example, and then we may give a more general definition. So I want to define this simple example on the blackboard, and I need to leave the microphone, but I will try to speak with loud voice. So let's refer, I think the two blackboards which I can use are, let me just check. And let me just check on, okay, perfect. So the position here is visible, perfect. I think this is fine. Let me refer to this very simple example. Let's just refer to a tank, okay? This is called bucket model or tank model, bucket model or tank model. It is applied in a variety of processes. Let me check if everything is clear. Yeah, on the video is not very clear. And also I think it's not very clear for you because you are very far. I hope you can see here. I tried to turn the light on, but it was not clear. So it didn't help much. So make an effort, and if you really can't see, let me know, okay? So this is a very simple model. It's, that is applied to a variety of processes. Let's apply it to model the case of the river flow. Let's suppose that this tank is representing the river, and we get over the river a precipitation, which is varying in time, which may be rainfall, maybe snow, it doesn't matter. It's precipitation, which means it's a mass of water. It doesn't matter if the phase is liquid or solid. It's precipitation that gets into the river. And into the river, we have, as I said, a storage. Let's indicate it with the symbol WT. And then we have an outflow, a river flow, QT. Okay, so the river gets water, gets precipitation. Part of it is stored, originating the storage, and part of it is released as river flow. We can write, therefore, the list of our unknowns here. Of course, precipitation is known to you because it's the input. If we don't know precipitation, we can't simulate any dynamics of water resources. So precipitation, we assume that it's known, while the river flow is unknown. So if you want to make a list of unknowns, it's QT, but also the storage is unknown. It's a second unknown. So let's write it here, WT, and this is a state variable. Okay, and look, these variables depend on time. Okay, of course, rainfall depends on time. Usually we express it as daily rainfall or hourly rainfall. It depends on time, and it's evolving, it's dynamic. So we need at least two equations here. Two equations. And if we want to use conservation law, we need two conservation laws. We may use, for instance, conservation of mass and conservation of energy. But let me just simplify the problem to make an easier introduction. Let's assume that the storage is constant. Okay, so it's something that is not relevant, can be neglected. So storage is irrelevant, not just constant, it's irrelevant, okay? Let's eliminate it from the list of the unknowns, and therefore we reduce to only one equation that is needed. We have an input variable, precipitation, an output variable, unknown, river flow. And you understand that in such a situation, it's very easy to write, if storage is zero, is neglected, it's very easy to write a conservation of mass law. It's very easy. If I get the system and storage is neglected, the output is equal to the inflow. This is my conservation of mass. So I can simply write that QT is equal to QT. And you may introduce, for instance, here, a coefficient. If you want, for instance, to account for a kind of water losses, okay? So usually this is what we do. Not all the rainfall is transformed into river flow. Part of it evaporates, and therefore you can introduce a coefficient in this relationship here. K may be equal to 1 if you don't have any losses, or maybe equal to 0.7, 0.8, it depends, okay? This is clearly a conservation of mass, which may account for some of the losses. It's clearly a conservation of mass. The mass of water that I get through rainfall is transformed in mass of water delivered by river flow. It's a very simple relationship, which, by the way, is linear. What does it mean, linear? Sorry if I spend time on concepts that probably for some of you are already well known, but I think these concepts have a very relevant implication, and therefore I need to make sure that you perceive not only the concept, but also the implications. What does it mean, linear? Linear, simply speaking, it means that if I make a graph of on the vertical axis, the river flow, and on the horizontal axis, I have precipitation. And if I suppose that K is equal to 1, This is the graph. It's a straight line. It's a straight line. Okay, linear function means that the relationship between river flow and the precipitation in this case is given by a straight line. But this is not really the definition. It is an implication of linearity. And if I want to give the definition of linearity, I think I already mentioned it to you, but let me write the two conditions. So if I have a function f of an unknown variable of a independent variable x that is multiplied by a coefficient a, this is the first condition, this is equal to a f x. And the second condition is f a x plus y is equal to fx plus fy. These are the two conditions for linearity. And in particular, the second condition is the superposition principle that we engineers know quite well. It means that you can sum the effect of two separate forcings. So the effect given by the combination of two forcings is given by the sum of the effect of each individual forcing. Now, why it's important that we know the concept of linearity? First, and more provoking statement, we need to know what is linearity because Earth system processes are typically non-linear. Okay, so we need to know what is linearity. Second, less provocative statement. Linearity is important to be known because it's very reassuring. It is easy to make predictions. If you have a linear model, if you have a linear system, you know, making prediction is easy. You don't have much uncertainty. Okay, the slope of the straight line may be uncertain. It is dictated by k, but you don't have a lot of uncertainties if the process is linear. And therefore, we are reassured. Or let me now just give you another example of a non-linear graph, of a non-linear function. Okay, so let me write it here, and then I delete it. Let's suppose that I have global temperature depending on CO2 concentration in the atmosphere, okay? What I know is that global temperature remains constant up to a certain concentration of CO2, and then starts increasing. And we know that at a certain point, we suspect that it may explode. This is typically non-linear. Even if it's a combination of linear functions, the relationship between T and CO2, given by this graph, is non-linear. To be correct, it's piecewise linear, but it's non-linear. And you understand, I am much concerned by such a progress because it indicates that there might be a threshold effect above which I get a sudden increase of temperature. This means that the process is unpredictable. This means that if I don't locate that threshold, I have a lot of uncertainty because, you know, because the rate of change here becomes larger and larger. So I am much concerned by non-linear processes. Climate is typically non-linear. There might be tipping points, threshold effects, but in most of the cases, we use linear models to represent climate processes. So you understand why it's important to know what is linearity. Because we understand the limitation of a linear model. So if you get information. I made this prediction. What kind of model did you use? A linear model. You know that there is uncertainty. So now your question may be, but if linear models are not appropriate, if Earth system processes are non-linear, why do we use linear models? Because they are simpler, because they are more robust, meaning that often they are very useful approximations. Okay, the first statement that I gave is linear models are simpler. You may say, I don't care if they are simpler. I want a model to be correct, not simple. Yeah, right. But there are two considerations to make. First, a simple model is less uncertain than a complex model. Uncertainty with complex models explode. Think, for instance, at a simple model that simulate only one process, for instance, temperature. And think of another model that, in order to better simulate in a more rigorous way temperature, also simulates rainfall, involves several more state variables. You understand, the number of equations increase, each equation is uncertain, and therefore the combination of uncertainties brings uncertainty to a higher level, which means that a more complicated model is more uncertain. There is no doubt on that. So using a simple model may be an advantage because uncertainty is reduced. The model is less precise, but still uncertainty is lower. Moreover, we will see that climate models are computationally demanding. Only few computational centers in the world can run global models of climate because of the computational demands, which means money, which means also CO2 emissions, because you know that supercomputers, they need a lot of energy. And therefore, simplifying models, it's a target. I have to avoid non-necessary computations. You have to avoid waste of resources, of computational resources, which means waste of resources in general. So this is why sometimes we use linear approximations, and sometimes they are preferred. Okay, now let's go back to our simple tank model. Let me also erase the other blackboard because otherwise I don't want you to get confused. Okay. Now let me gain some room here by removing the definition of linearity. I think you got it. It's in my lecture notes somewhere, not precisely in this one, but you will get through the lecture notes the definition of linearity. By the way, it's very easy to find on Wikipedia. Okay, and the definition of linearity, please take into account that it's important and it's not difficult to remember, so it's not a challenge to remember it. So please make an effort to store it in your mind, because it's extremely important if you want to be able of talking of climate. You need to know what is linearity, believe to me. Okay, so now let's remove the simplifying assumption that we made, because it's not realistic. If you think of a river, you can't neglect the effect of storage. So it's not realistic. So let's move a step forward in making the model more rigorous. Okay, so let's cancel this representation here. And let's remove this assumption. Storage is important. Okay. So if we want to model storage, first consideration, we need two equations. And as I said, let me think about conservation laws. With a picture like that, with a scheme like that of a tank, it is quite obvious to resort to mass balance. We already used mass balance in the previous example. Let's now to write mass balance by taking into account the change in storage. Okay, so mass balance here, mass balance. Okay, the difference between precipitation minus river flow is not zero. It's not zero, because in the previous example, it was zero, okay? Now it's not zero. It's equal to the change in storage. This is quite simple, even if I introduced the nasty derivative. The derivative is a change in storage. And it's quite obvious, if you have less precipitation than river flow, so that you have more input than output, you have an increase in storage. You have a change in storage, it's an increase. And the increase in storage is noted here with the derivative, which is a difference. The derivative is a difference. It's like if I want to write storage as a function of discrete time. If I want storage at time 2, for instance, this is equal to storage at time 0 plus storage at time 1 minus storage at time 0. Let me just stop to 1. Okay. So if I want to write the storage, because I wanted it at time 1, it's equal to storage at time 0 plus the change in storage from 0 to 1. And this is precisely the derivative. The derivative is just a difference, describes the change in storage from 0 to 1. So this equation says that, okay? So this is conservation of mass, or it's also called, as I said, continuity equation. And there are other names because it has a lot of synonyms like conservation of mass or conservation okay. Let's stop here because I don't want to give too many synonyms, but it's a very known principle through which we can describe many processes, especially those that imply transport, okay, transport of matter. But here we have two unknowns because I have only one equation and I have two unknowns, Q and W. So I need a second equation. I need a second equation because I introduced a state variable. Okay. And what kind of second equation I can use? Okay, again, the laws of physics, again, the conservation laws. I could write conservation of energy, which is the correct, theoretically based second equation to consider. Why it is the correct one? Because when you have processes where there is movement of a body, in this case, the body is a fluid, this movement is originated by an exchange of energy. In particular, here, I need a relationship between storage and Q, storage and river flow. It's conservation of energy. Storage is potential energy. If you think of a reservoir, water doesn't move, is fixed, doesn't move. But there is a lot of water into the reservoir. It's a lot of potential energy. Downstream in the river, you have not much potential energy because the amount of water stored into a river is reduced, but you have the water running, so you have kinetic energy. So the movement of water from the output of the reservoir through the river, what happens here, is regulated by an exchange of energy. So conservation of energy is fine. I can apply conservation of energy. On the other hand, I could also apply an empirical equation. An empirical, any form of relationship between Q and W is fine. And in this kind of model that I am now talking about, the bucket model, usually, for simplicity, we adopt a second equation, which is a relationship of this side. It's WT is equal to a coefficient A times UP. It's a linear relationship between storage and river flow. And it's an empirical equation. It must be equivalent to conservation of energy because, as I said, there is an exchange of energy originating this movement. But this is empirical in nature, it's linear. And we use a linear equation here for the very reasons that I mentioned before, simplicity, etc. And now I can combine these two equations into a system. That's fine, I can solve it. Two unknowns, two equations, I can solve it. Now, a couple of considerations on what I have written. I have written a system given by two conservation laws. One is physical, conservation of mass. The other one is empirical, but it's equivalent to a conservation of energy. Good. Now, let's look at the form of these two equations. This is a system of differential equation. When you have one derivative, at least one derivative, into an equation, the equation becomes differential. And when you have a system with at least one derivative there, then it's a system of differential equations. And why did we need to introduce this differential, this derivative? Because we wanted to describe storage. If you remember the previous form of this model, it was PT equal to QT. There was no derivative. There was no derivative because we didn't want to describe storage. When we describe storage in a conservation of mass, we need to introduce a derivative. And when we want to describe storage in any conservation law, we need to introduce a derivative. You understand why? It's here, because it's input minus output that gives a difference, and therefore it's a derivative. So this is why Earth system models, climate models, are made up by differential equations, because they are based on conservation laws. Of course, we get a bit concerned by conservation laws because there is the derivative. And any student, any scientist, any researcher is concerned by derivative and the integrals. Why are we concerned? Because we associate the operation of differentiating or integrating to complexity. And this is justified because in our background, in our previous experiences, we learned that computing integrals is not easy. There is an heavy mathematical development. But actually, if you look at the derivative that is here, it's just a difference. Look this equation. It's a sum. It's a sum. Here, what I brought here, W1 is equal to W0 plus the difference. It's an integral. The integral is a sum. The derivative is a difference. It's very simple. The concept is very simple. The computation is complicated. But today we can use numerical integration with some caveats, because sometimes there is numerical instability, but we can use numerical computation So numerical computation just reduces the integral to a sum and the derivative to the computation of a difference. We don't have to be concerned. Strictly speaking, in order to understand what these models do, we don't need to be able to compute the integral analytically. We need to understand what is an integral, but if we cannot compute it, it's not a problem. It's really not a problem. So you don't have to be concerned. But you have to know that it's a complication, of course, but it's a complication that we can't avoid. And also note one thing. Here, in computing the sum, which is an integral, as I said, I needed to know W0. So when I want to get the integral form of the variable of the storage, when I want to compute the integral because I want to compute the storage, it's not just enough that you sum the differences. You need the initial value. And this is the initial condition. Okay, when I integrate a long time, I need an initial condition. So this is why we know that to compute an integral, I need initial and boundary conditions. What are the boundary conditions? When I integrate over space, the boundary conditions are the condition at the contour of the space where I am integrating on. Okay, so it looks complicated because if you look at the system of equation of a climate model, it's amazing. I mean, it's one full page of equations and people don't even publish them because it's extremely complicated. But actually, the concept is simple. Conservation law that must be written in differential form because I want to account for storage, and therefore I get this complication, but it's a purely analytical complication. It's not really operational. Of course, in order to compute all of these integrals, all of these sums, I need a supercomputer. A supercomputer that is taking sums, basically. But it's a supercomputer because I have many equations. And also we will see how they are structured, these global models. They are indeed amazing for the number of equations. Okay, so given that we understood now with this very simple example what conservation laws are, let us explore a general definition of conservation laws. I think it is interesting, and look, I may ask you at the exam some basic questions on conservation laws. I will not ask you the mathematical development. So you don't need to remember, let me scroll down. You don't need to remember the equation that you see here. Let me see if I can expand it. You don't need to remember the equation that you see on the screen. I may ask you some general questions like what is a conservation law, or in the quiz, because you know that your exam is a quiz. So maybe what is a conservation law, and you have 5 possible answers, only one is correct. So when you remember the definitions, that's fine. I may ask you what is a state variable. I may ask things like this, or I may ask you a question like, for what reason in Earth system models we need differential equations? And you have alternatives to select from, okay? But I want, anyway, to illustrate to you the general form of a conservation law. And in its general form, the conservation law refers to an arbitrary volume V. Look at the sketch up there. It's an arbitrary volume of space. And this volume is located, it's maybe moving in space. It's not necessarily fixed. Maybe a volume that is moving. But if it moves, in order to support the derivation of the conservation equation, must move without acceleration, must be an inertial frame of reference. Once again, I will not ask you a definition for an inertial frame of reference, but I think this information is useful to you, depending on your background. Inertial means that this volume may be fixed or may be moving with constant velocity. Constant velocity in vector is not changing the direction, constant velocity. It's an inertial frame of reference. For simplicity, let's suppose that the volume is fixed, okay? And the volume is contoured by a surface, S. So the example is very similar to the tank, but the tank has a precise form and has input only through the open upper part and output only from the bottom discharge. In this arbitrary volume, the flow can pass through the whole surface S, contour surface S. I may have flow entering into the volume of any quantity through the surface and flow out from the volume through the surface. Now, let's indicate with the ds a small piece of the contour surface, and let's indicate with n the normal outward vector to ds. Okay, and you will see I need to split the surface in pieces to account for the spatial variability of the flux through S. Okay, so in a narrative speaking, what are the reasons why an arbitrary quantity within volume S may change? This arbitrary quantity may be mass of water, like in the case of the tank, but maybe also energy, maybe whatever, maybe heat, okay? So what are the reasons why we may have a change within the volume V of the total quantity? This total quantity here is called capital phi, with the symbol here. Let me take some room here. With the symbol P, or P, sorry, I couldn't make the symbol in the equations equal to the symbol in the text because I made a mistake. I will fix it, okay? Be patient, because this is a new text that I made during the weekend. And but with the symbol, anyway, capital phi, I indicate the quantity, the total quantity within the volume S, maybe, as I said, mass, energy, heat, whatever. And I indicate in the lowercase p the density. So this is total quantity. Total in B. And this is the density. Density in B. Density is quantity divided by volume, and in general, I assume that the density may be varying within the volume, okay, depending on space, depending on the location, here and there, it can be varying. In the equation that you see on the screen, I don't explicitly indicate the dependence on space, which is the dependence on x, y, z. I'm not explicitly indicating it because I want to simplify notation. But keep in mind that when we talk about, of Earth system processes, usually the variables are varying in space and time. Okay, there might be exceptions like global temperature. Global temperature is not varying in space, it's global. It's varying in time, but not in space. But if I want to model the temperature over the globe with the spatial variability, it depends, of course, on the coordinates x, y, and also z, because if I go up, temperature decreases, etc. Okay, so capital phi is the total quantity, lowercase v is the density. So what are the reasons, once again, why I may have a change of the total quantity, capital phi, within the volume? There might be a source, which means that internally I have a source. And this is represented by right-hand side, It's represented by the last term, the third one, the third addendum. You see that you have a variable called h. H is a source of the quantity, source of capital phi per unit time and unit volume. And by computing the integral over V of h in the V, I want to compute the contribution of the source term in the volume. Why there is an integral here? There is an integral because I assume that the source may change in space. And therefore I need to sum, I need to divide, to split the volume V in small pieces, the V, of infinitesimal size. And I need to compute the integral to sum all the sources in each single piece. So I have this volume, V, okay, V, and I split in many subvolumes, and these are my dVs, okay, this is the dV. And then I want to each dV compute the source term, and then take the integral, which means summation, okay? I sum all the contribution of these mini blobs, mini volumes. And this is this integral here. And you see the plus sign, because it's a source term. Now, let me jump, because I forgot to introduce it at the beginning. At the left-hand side, what is on the left-hand side? I have on the left-hand side the variation in time, the change in time of the integral over V of the density in the V. Okay, and then the sign. So what is this? This is the integral over V of density times volume is the total amount, is phi. This one is phi. I said density is not homogeneous. I allow density to be varying in space, and therefore this is why I need on the left-hand side to put an integral. But this is equivalent to the change over time of the total quantity, capital phi, which can vary. Now we look at again at the right-hand side for the source term. We already discussed it, and then it can vary. The total quantity phi can vary for flux of the total quantity through the surface S. And this is why you see there the integral over the contour surface. And this flux can happen for two reasons. For transport, meaning that from within the volume V, I have a movement of fluid, bringing the quantity out. So it may be, for instance, for the case of the bucket model, it may be water flowing out. It's due to transport. So there is a flux that is due to transport, which is given by the second term at the right-hand side. And how can we recognize that is due to transport? Because there is a velocity v, lowercase v. There is the velocity term. The velocity term means that it gives a transport. If I compute density times velocity times the S, I get the change in time of the total quantity. And then we still have one term to discuss, the first term at the right-hand side. This describes the flux through the contour surface in absence of transport. And for instance, let's take the example of heat conduction. Heat conduction, it means that you have heat from inside the volume that can go outside, even in absence of transport, for conduction. So the capital F is the flux of the quantity through the contoured surface per unit surface and unit time. So basically, this equation looks very complicated, but what it says is, whatever is the quantity I want to make to apply the conservation, whatever is the quantity that I want to conserve, and whatever is the control volume, the change in time of the quantity is given by a source term and flux through S, which may happen for transport or even in absence of transport. This is the very general form of the conservation equation. And it's also a simplified form of what is called, for your information, it's not something I will ask you, what is called the Reynolds transport theorem. It's an essential component of climate models. So your question could be, but if this is general, can I get my bucket model, which was in the blackboard before, from this equation? The answer is for sure yes. Because if you look at the left-hand side, this is change of the quantity over time is W, what I called earlier, it's what I called earlier for the bucket model, I called it derivative of W with respect to T. So the left-hand side that you see up there, for the bucket model is this derivative. Of course, you see an integral there, and here it's already computed, because storage W is already the integral of the density in the volume. So this is what I got before. And then let's forget about the source term H, the last term in the right-hand side. Let's forget about it because it was not considered in the bucket model. And let's also forget about the term F, capital F, because we didn't consider a change of storage in absence of transport. We only consider the second term, the middle term at the right-hand side. And it was given simply by minus with the integral already computed, because through the contour surface of the bucket, we admitted only two flows with transport, precipitation that gets into the bucket with a flow, with a velocity, with whatever, and flow, outflow, which of course, it's a flux through the contour surface, precisely through the bottom discharge, given by a velocity. And that's it. And this is perfectly equivalent to what you see up there with the appropriate simplification. In general, this is something that we always do. We start with models from a general form of equation, a general physical law, and then we simplify it accordingly to our needs and our decisions regarding model complexity. Just let me check if here you can find in my lecture notes the sketch of the bucket model, okay? And you see that there is the equation explaining that from the general formulation, you can get to Pt minus Qt, what I put on the blackboard here. And then there is another box, which is application in continuum mechanics. It is a development that brings us to elaborate the equation that you see on the screen now, just 1 second, this equation, to elaborate it and put it in a more simplified form for the case of continuum mechanics. So for the case where the property capital Phi within the volume is varying in according to a continuum equation, a continuous equation, sorry. And therefore you get different forms of it. And in particular, what you see here, number 6, it's the way in continuum mechanics the conservation laws are presented. I just wanted to put it on the screen and in your lecture notes in order to give you an additional information. No need to study these further developments for your exam. Okay, so we dedicated about some more than 1 hour to a very, let's say, to a mathematical discussion. And now I go back to the narrative form. During this course, there will be some parts that will be dedicated to maths. I would say that not more complicated than today, and other parts more narrative. So first 2 lectures were essentially narrative. This one is, half of it is more mathematical, and now I go back to the narrative form. But I just wanted you to know, because this is a request that I got explicitly last year, I just wanted you to know some more on the mathematical structure of climate models. Last year, at the end of the course, in the surveys of the students' opinion, which I study with great interest, somebody said, I wish we talked more about models, how they are structured, how they work. So I decided to take this suggestion, and I am introducing, I will keep the exam more or less like last year, but I will introduce some, I am introducing some more on modeling. And an interesting thing that, I mean, interesting, a thing that I believe is interesting in what I said is that, let's go back to the scheme here, is that this equation describes through integration, you see that the equation has integrals over the volume and over the contour surface. By integration, by integrating, we lose the information on the spatial variability within the volume. We have information. We said that density, and it's spatially variable within the volume. And also the source term, but also the F term is spatially variable. This is why we put this term under integration. These are spatially variable. This information is lost through integration. What we compute is a sum, which is an average. So the quantity phi that we derive at the left-hand side, it's a quantity that is averaged over the volume. So with this approach, by studying these conservation laws on this volume V, which, by the way, I forgot to tell you, is called the control volume. Control volume. Okay, it's the volume over which we extend our equations, our modeling. So by integrating in this equation, we lose the information within the control volume. We only compute an average value of phi. On the other hand, I said that there is heterogeneity. So this means that if I want to minimize the amount of information that I lose, I need VB very small. I repeat, I need the volume V, the control volume B very small. And in general, this is what we do with climate models. Sometimes you get somebody saying the resolution of the climate model is 5 by 5 kilometers. I want to give you the means to get the concept, to get the meaning. Or the resolution is 25 times 25. It means that the control volume V, each of the control volumes has that size. And of course, 5 by 5 means a surface, which is extended to the atmosphere above it. So it's indeed a volume. So again, if I want to model heterogeneity, the finer the resolution, the better. 25 times 25, it's a bit coarse, it's a bit rough. 5 by 5 is okay. But now efforts are being made to simulate at a resolution of 3 by 3 kilometers at the global level. So what is the result? The result is, I move to the next lecture, climate models. The result is what you see here, just 1 second, because, okay, the result is what you see here. This is the composition over the blog, over the world of my control volumes. And in this case, I don't know what resolution is this one, but it's much more than 25 by 25, okay? And you see that the control volume includes the surface, 25 by 25, for instance, plus a piece of the atmosphere. And if needed, I may extend other control volumes in the upper sections of the atmosphere. So the result is what you see here. It's millions of control volumes, millions, literally, which means millions of equations in order to describe heterogeneity. You are not obliged to do that. You can also split in only few control volumes, or you can use the globe as a control volume if you want to model a global variable, global temperature. There are very simple climate models. We will see an example that allows us to model global temperature with one single equation. But if I want to model heterogeneity, I need to make this subdivision in slices of the globe, thus obtaining millions of equations. And unfortunately, the problem here is that to describe the flux through the surface of each one control volume, you need to know the output from the neighboring control volumes. So you cannot solve any control volume individually. You have to put together a system of millions of equations to be solved simultaneously. Once again, this is why you need supercomputers. This is why only few computational centers in the world can make it. You know that in Bologna now we have 2 supercomputers, the one of the ECMWF and Leonardo. And this has been a great achievement. Now Bologna has really a super computing capacity, but I'm not sure if you visited inside what is a supercomputer. A supercomputer means a huge room, much larger than this one, that is full of processors running simultaneously with a lot of noise, a lot of heat, and you need air conditioning, you need a lot of energy. They have a power generator that is amazing in terms of power, which means really a computational capacity that is highly demanding. This is why climate models couldn't be applied 50 years ago. This is why it's a relatively young science. And also you understand why we have uncertainty. It's clear. When you put together millions of equations, each one of them may be a little bit wrong, and you put together all of these little bit wrongs, you get uncertainty. And the model needs to be optimized. What does it mean? It means that in some of the equations I introduced, you saw a coefficient k. These coefficients can assume different values. You need to estimate, to find the best values for this coefficient. It means optimizing the model. These coefficients are called parameters. Parameters. A model counts, an Earth system model, most of them count parameters, include parameters, and we need to optimize them. And you understand what kind of effort is this one, what kind of modeling effort. And now we have the concept of the digital twin emerging, meaning that we want to create a digital replica of all Earth system processes, not only climate. We want to replicate with a digital twin everything, possibly everything. I mean, water cycle, close to the climate dynamics, and in conjunction with the climate dynamics. And then we want to model ecosystems, because ecosystems are clearly much relevant for climate. It's a dream, it's not reality, it's not yet reality. And also in terms of climate, it's still a dream, because we know that our predictions are not rigorously correct. There is uncertainty, so it's a dream. And even when we try to reproduce the past climate with these models, we get mixed results. A global model typically works well in some regions and not as well in other regions. So it is extremely important when you download data from a global model, it's extremely important that you make checks, that you check the reliability in the region you are interested in. And you, of course, have a contingency plan for dealing with uncertainty. Still, these models are amazing. I mean, it's a major achievement. And in the long term, no doubt that will improve and improve and improve. Think of meteorological models. If you go back in my youth, when I was like 40 years ago, the meteorological predictions were just fun. People was looking at there and making fun because they said that they are always wrong. Now we have meteorological predictions that are fairly accurate with a lead time of maybe 2 weeks, in some cases 2 weeks, when there is a stability in the atmospheric system. They extend prediction in 2 weeks. This was absolutely not possible 30 years ago. 30 years ago, people were climbing mountains by just looking at clouds and the weather. And they in the morning woke up and said, who knows? And they went. Now, it's a risk that it doesn't exist. Even in a mountainous region, you look at the forecast of the weather, and if they say that the weather is good, it's good. And if they are not sure, they tell you, look, I think it is good, but I'm not sure, which is perfect. It's perfect. And it is an amazing achievement. Meteorology, and meteorological prediction, I think it has been an amazing achievement in 30 years, because 30 years ago, I am sure, I tell you, the meteorological prediction were still in their infancy. So I am sure that even for climate, we will make progresses, because I think we will have more computational capacity. I don't think we will increase with the same rate in terms of computational capacity as the past 20 years, because indeed it was amazing. 20 years ago, we had to change the personal computer after 2 years, not because of other problems, but because they became obsolete in terms of computational power. Now it's not a problem anymore. We are getting to a dome, let's say, but I am sure that we'll continue to increase. So the supercomputer in Bologna, I think it will take a long time before becoming a personal computer with the same capacity, but for sure, it will increase its demand in terms of energy, in terms of space, whatever. Good. So let's focus on climate models in this lecture. Let's start. And first of all, what is our purpose? We can split our purpose in climate change mitigation and adaptation. And you already know because we already defined them. But I just want to remind you, mitigation means that we try to mitigate climate change. Adaptation means that we adapt to it. We accept climate change and adapt to it. And there are two links to Wikipedia here, which you may want to explore. And mitigation takes a long time. Adaptation, it's not so long. Adaptation may take the time for building a strategy and building an infrastructure. But it's not a very long time. Mitigation may require 100 years. We don't know, actually. What we could see is that 1 year of pandemic was not sufficient. So 1 year of very low CO2 emissions was not sufficient to induce significant changes in climate. It means that mitigation, reduction of emissions needs to be applied for a long time, and also the effects will take a long time. Also, the past history of the Earth suggests that the reaction of the climate to volcanic eruptions or to other perturbation is quite low. It's quite slow. And mitigation also is global. It needs a global action. So it is dealt with by international agreements and by the involvement of several governments. Adaptation is local, and it's a responsibility of the local administration. Ideally, as I already said in my introduction, we should combine the two, because in this way we can integrate the two different time scales, two different spatial scales. So integration is the ideal solution, but on the other hand, we don't have enough resources, because both of them cost a lot of resources, not just money. Some of them may cost resources in terms of cultural heritage, in terms of space that we lose, space meaning geographical space. And some think of solar farms. They require land to be dedicated to them, which means that we may lose land for food production. So it's not only a matter of money. This is our purpose. And for this purpose, for achieving this purpose, we need predictions, or we need future climate scenarios that are computed basing on input data drivers, which we already discussed, by the way. So the history of climate models, it's not really recent. I said that global models have a relatively short history. Actually, there is more to say on this subject. The global models, as they are structured now in a grid form with millions of control volumes or billions of control volumes, indeed, they are recent because they require significant computational capacity, as I said. But actually, the history of climate modeling began with very simple models applied at the global level, and which have already quite a long history. And for instance, if you think at the Greek astronomers and geographers, and they understood the shape of the Earth, they connected climate to the inclination of the terrestrial axis. They did that by elaborating a first preliminary and very global climate model, because they understood, they elaborated a conceptual scheme that demonstrated that with the varying inclination of the Earth's axis, different portions of the globe get more solar irradiance. and therefore could explain changes in climate in this way. And this is ancient Greece. So there were, and also there were simple models that were developed in the 19th century, which were based on radiative energy balance and radiative transfer. I will show you some examples. Let me just, before I move forward, let me get the PowerPoint presentation of this lecture. 1 second. Because it's better if I, oops, sorry. It's better if I show the PowerPoint presentation here. Okay, here we are. And then in the 19th century, I said, and I will present to you one of these models. It's very interesting. And then we started in around 1950, when the first computers became available with a computational capacity that was infinitesimal with respect to what we have now. But people started to elaborate simulation models of the entire atmosphere with some spatial variability, by taking into account to some extent spatial variability. And then from 1990, there was a coincidence of the onset of global warming and the availability of computing power. So starting from about, as I said, 35 years ago, we started to have available a lot of computing power, and which suggested to study Earth system processes through numerical and high resolution models. I tell you that the same opportunity was considered for modeling the water cycle, and indeed, even in hydrology, so water cycle modeling, people tried to apply very high resolution models. Now this idea has been partially dismissed, and now people are more oriented towards simpler model for modeling the water cycle, because it was understood that for practical technical applications, water cycle modeling, hydrology is close to engineering. It was understood that for technical applications, uncertainty management with high resolution model was very challenging. So the idea of the high resolution was dismissed, at least in part. If you look at the literature, scientific literature, you don't have to, but if one looks at the scientific literature in hydrology, this is clear. So I wonder, and I discuss often with the colleagues, if climate science is going to follow the same route, because climate science is now aiming at modeling at a finer and finer resolution, with the result that it becomes more uncertain and more less diverse, less accessible, less diverse, because when you have only less than 10 computer centers in the world that can make such simulations, you understand that there is not much room for diversity. I have noticed in water cycle modeling that when it became accessible to several countries and even to universities and researchers with a limited amount of resources, still the field gained a lot from the contribution of some pieces of diversity that was not possible before. So I think that today maybe that climate science is a bit suffering from that, and I'm not saying lack of diversity, but a reduced diversity. And I think that science can really progress when it's available to a large number of people, and the history of the open source communities is clear in that respect. But as I said, probably we will get there. Okay, let's make a 15 minutes break. And so let's start again at 4:30, a few minutes later. Thank you. And if you have any question, okay, you may ask also questions later, no problem. Okay, I am ready to restart. Sorry, I was 5 minutes late for a commitment. Okay, so we already talked about the spheres. Sorry, we already talked about the spheres of the Earth system. So we are not talking of the left-hand side, left part of the slide. I just want to draw your attention on the picture on the right part of the slide, which describes the various layers of the atmosphere, starting from the troposphere, which is the layer in the range 0-12 kilometers from the Earth's surface. And then there is the stratosphere, the mesosphere, thermosphere, and exosphere. Just beware of these terms because we are talking of climate in this course, and therefore, of course, these are terminologies that are very recurrent, and it's important to have clear in mind that the first layer is the troposphere. And it's the atmosphere, as we know, is these layers contain a mix of gases, and we commonly call this mix air. It's retained by the gravity force, and here we count 5 main layers. And we know that there is, among these gases, there is the CO2, which is playing a relevant role for several processes. We are interested, of course, in the greenhouse effect. And CO2 is not the only one greenhouse gas. There are several of them, including methane, including others, but it is one of the most important. One relevant greenhouse gas is water vapor. This is also an interesting notion to learn, but CO2 is one of the most important because we know that the concentration of CO2 in the atmosphere recently, and in particular during the global warming period, is increased. Okay, so this is once again a discussion on the spheres, and I drop it, but please have a look and remember these definitions, which could be also the subject of some questions during the quiz. And it's particularly interesting to point our attention once again on the technosphere. Sometimes it also referred to as anthroposphere, and it's the sphere that includes the human activities. It's the part of the environment that is made or modified by humans for use in human activities and human habitats. And this is a new concept. It's a new concept like the new concept of the Anthropocene, which is it is a proposal to name the current era Anthropocene because it's a period, it's the period where the effect of the human activities on the Earth system became essential, relevant. There is a lot of discussion on the definition of anthroposphere, Anthropocene, the introduction of the term Anthropocene, and there is discussion because usually the geologic periods, the eras, are determined based on geologic signatures, and we don't have a geologic signature of the human activity. So there is some discussion, but the concept is clear. One important thing is to have a good perspective of the distribution of water over the Earth. This is a very classic picture that is public domain. You can find it in several websites. Some of the information that is reported here is well known. So we know that the total amount of water over the Earth is unchanged from the beginning of the history of our planet. So mass of water is conserved. And we know that about 97% of the total water available is salt water. It's water into the oceans, let's say. And in total, the salted water is around 97%, and fresh water is only 2.5%. You can see these numbers in the left column over there. Now, if we zoom on the fresh water distribution, and the zoom is reported in the middle column, we see that a lot of fresh water is stored in glaciers and ice caps, and almost 70%, and therefore is not usable. And then we have groundwater, which counts on about 30% of the fresh water, which means 1% of the total water. And here you see the great importance of groundwater, the great importance, and you can also understand the key role that groundwater plays for sustainability, because groundwater is indeed a relevant water source for several countries. And we have a big problem with groundwater. With groundwater, we cannot estimate the available volume. So you may say, how did you determine this percentage here? Because we are talking about volumes. This is a guess. This is a guess, and which is based basically by computing the difference from estimates of water in the ice caps, which is more easily quantifiable, and fresh water, surface water. So the difference, we believe, it's given by groundwater, and we can get rough estimates. But when, especially at the global level, it's relatively easy. But when we get to a groundwater body, a groundwater aquifer, and we have the need to estimate the volume of water that is available there, this is a question without answer. And we still don't have the means to estimate the volume of groundwater in the aquifers. It may seem amazing that we have such level of uncertainty on a so important resource for sustainable development, for everything, but this is the reality. So we can monitor the status of groundwater bodies by looking, for instance, at the pressure in the bodies, by looking at the level of water in the wells. But the very precise question, what is the volume of groundwater that I can extract from there? And what is the recharge time? These are questions without answer. And then we have surface water. It's about surface water, other fresh water. It's about 1.2%. Okay, let's explode this 1.2% in the right column. So we have some surface water that is stored in ground ice and permafrost. This is different from ice caps and glaciers. Permafrost is ice that is stored within the rocks, and ground ice is the ice that is present over the ground only in some seasons. It's not ice stored in the ice caps and in glaciers. And this is about 2/3 of this 1% of fresh water. And then we have lakes. It's quite a significant storage. And then we have soil moisture. It's about 4% of 1% of 3%. And then we have rivers, it's negligible. And living organisms, it's even more negligible. So by looking at this picture, you may get the feeling that rivers are not relevant for water resources. This is, of course, not true. And the reason why this is not true, despite the low percentage that you can see here, is it's the main limitation of this figure. This figure is a static representation. Basically, if you took a picture of the Earth system and in particular of water into the Earth system, at a certain time, you estimate these quantities, these percentages. But this picture, being static, doesn't take into account the flow. Rivers, in terms of volume, are insignificant. In terms of flow, they are very significant. So it means that if you compute the volume of water that we take from rivers in order to satisfy our requirements, it's much higher than this small percentage, because the volume is low, but it's completely replenished. So while groundwater is a huge volume, but it's not replenished in a short time scale. So if we get it, it's hard to wait for the recharge. The river, when we get the water, is immediately recharged. So rivers are an essential source. So when you talk about water resources, you don't have to consider only the static picture. We should also consider flow, which is not depicted here. So if we look at flow, we see that rivers are not a huge concern. Even if we take all the water from a river, it's replenished immediately, or at least in the span of a season. If we take all the water from groundwater, this is a big issue, because it takes a long time, maybe thousands of years, to recharge. Today, we are using from the groundwater bodies some fossil water. Fossil water means that you can estimate the age of water by analyzing the isotopes. We will talk about isotopes later. And we know that this water rained about thousands of years ago. It means that it may take thousands of years to recharge it. So understanding water distribution, understanding the water cycle is essential. And the water cycle is an essential component of climate models. Unfortunately, in most of the up-to-date models, it's reproduced in a simplified form. And this is, again, a problem. Okay. So these domains, water cycle, etc., are open systems, meaning what? A closed system is like the Earth system, is a system where you don't have any input or output of matter. The only thing that can get into and out from a closed system is energy. If we look at the atmosphere, the system is not closed, because the atmosphere can get water in the form of vapor and can also deliver water over the Earth's surface through precipitation. So these are open systems that are tightly related to each other, with exchanges of physical quantities: mass, heat, momentum, energy. Remember that the climate system is driven by solar energy. And remember that this heat, the dynamics in terms of heat, is what governs the temperature of the Earth. So as I already pointed out to you, it is essential for us, if we want to build a climate model, that we understand these connections, these feedbacks, and these links in general between the different spheres, between the different systems. And we may decide to model only one sphere, and the connections are given through boundary conditions or through fixed inflow, outflows, or we may decide to model the system as a whole. Today, we are still in the phase where we don't want to model the system as a whole, because we don't have the capacity. We don't have the computational capacity, but especially we don't have enough information. Okay, I think I can skip this, because this is a narrative of several exchanges. I think that let me just discuss a little bit the first bullet point. Earth is heated by the sun is in an uneven way. Some parts of the Earth receive more energy, and therefore we have temperature differences. We know that. And the system tends to reduce these differences by transporting heat from the tropics to the poles. And this transportation of heat gives rise to ocean currents, winds, evaporation, precipitation, and global weather patterns. Why I wanted to point out to you this? Because the description of this transportation phenomenon is essential in order to describe the climate. And in particular, to describe ocean currents is much relevant. To describe, so climate models contain a submodel of the ocean system. They need to model also ocean circulation. And I want to give you an idea of why this is challenging. It is challenging because to describe the water flow into the ocean, you need a lot of information that is not readily available. And the most relevant information that is not available is inflow into the ocean. We get inflow into the ocean from rivers, but we get also inflow from the land in the form of groundwater flow. We have a movement of groundwater resources from the land to the ocean for the very reason that, I mean, the precipitation is located at this water over the land is higher in altitude. So if we don't use it, if it doesn't evaporate, the excess water reaches the ocean through the rivers and groundwater flow. If it is already difficult, if it's already a problem to take into account, to quantify the global river contribution to the oceans, it's nearly impossible to quantify the global groundwater contribution. So we don't have a clear idea of these groundwater fluxes. And they are playing quite a significant role. And if in an ocean model you increase the groundwater flow, you obtain different results, and the climate is behaving in a different manner. This brings us to notice that even some kind of human activities, which we think may be less relevant to climate, like groundwater extraction, may have an effect which we cannot quantify over the whole system. But if we want to build a climate model, we need to quantify it. And we can take a simplified approach. We can make a crude approximation, but still we have to represent it. Now, we already talked about turbulence and the chaotic behavior of the system, the famous butterfly effect, which we already discussed. And the butterfly effect means that, you know, if a butterfly moving a wing in Japan may originate a tornado in the United States. Of course, this is not strictly speaking true, but it gives the idea. So when I talked about integral, initial and boundary conditions, you understand a climate model needs an initial and boundary conditions to run. For instance, if I run the climate model starting from 1800, I need to set an initial condition. And this initial condition is the value at time zero. This initial condition, in the presence of chaotic behavior, may explode, meaning that a small change in the initial conditions that is transferred over millions of grid cells may originate a drastic change of the final results. So the simulation of weather in the United States is much different if in Japan I change the initial condition of an epsilon. of a tiny quantity. This brought Lorentz to say chaos is such that a butterfly flapping a wing in Japan may trigger a tornado in the United States. And chaos is extremely important to consider, and it's the effect of turbulence. And you see here on the right in the picture, the effect of turbulence, indeed. Okay, now I think that I can skip this because I already introduced the purpose of climate models and their structure. And here, once again, it is reminded that these equations of GCM, what are GCM? Global Climate Models. It's an acronym that is widely used. It's widely used to mean it's an identification, an acronym for climate models, global. And GCM are, there is another category of models, local models. So GCM are global. The local models, meaning that they aim to reproduce only a small portion of the climate system, are called limited area models, LAM. Limited area models, they are not discussed here, but being more focused in space, count a reduced number of control volumes, grid cells. So they are simpler. They require less computational efforts, and therefore they can run on a finer resolution with respect to GCMs, provided we have the information necessary. Because, you know, for each control volume, you need a set of variables, input variables to be provided. Actually, the procedure that we usually follow is to run a GCM, a global climate model, to generate the initial and boundary conditions for limited area models that can only run for a smaller time span and a smaller spatial domain. I talked before about the size of the boxes. What you can see here, it's the mention that modern models have a box size varying from 100 square kilometers, meaning 10 by 10, to 600 square kilometers for coarser representations. Actually, this is 4 years old, because now, as I mentioned to you, we are already available for Italy. We are producing now for Italy, and I think it's already available, but it's under production. The 5 by 5 simulation, which means 25 square kilometers, and we are in the progress of looking for a setup to generate a 3 by 3 simulation. And this is run over limited portions of the globe. Typically, the size of Italy can be covered, to give you an idea, with the modern supercomputers. So I think that I already mentioned this. Don't be surprised, because when I talked about the bucket model and the conservation laws, I made several considerations on the need to reach simplifications, to simplify. And these considerations are not given in the corresponding web page, are given here in the web page that I'm reading now. So I gave an anticipation of the discussion on climate models that we can find now here. I think that we can skip this slide because it's already it was already discussed, and I think that this slide requires some discussion because there is some new information. First of all, it's talking about input data, and input data indeed they are a challenge because these input data need to be given at the scale of the grid. So if one input is solar irradiance, you have to give solar irradiance at the scale of the grid. If the grid is 3 by 3 kilometers, you need to give solar irradiance at the scale 3 by 3. And this information is not always available. What we do when it's not available, so let's suppose that solar irradiance is given to a resolution of 10 by 10, what we do is that we assume the input variable, the considered input variable constant over the size of the coarser grid. So if solar irradiance is only given at the size of 10 by 10, it means that I have 9 cells 3 by 3 within a 10 by 10 cell, and I assume that over these 9 3 by 3 cells, everything is constant. This is a simplification. Of course, it's an assumption that is not verified. I mean, for some variables like solar irradiance, it's fine because it's not much heterogeneous. If you have heterogeneous variables, it may be a problem. And let me give you another example. The urban settlement. Now there is an increasing interest for urban climate models that can simulate the climate within a urban area, which is different from the outside climate because there is less wind, so the temperature is higher, and also there is more reflection of heat by the buildings, there is less infiltration, less evaporation, several things. But in order to make a climate model working at the urban scale, you need a resolution like 1 by 1 kilometer. It's already a bit too much, it's already a bit coarse, but 1 by 1 kilometer is fine. So what people do usually is to run the model, limited area model, with the scale of 1 by 1 kilometer. That's fine. The problem is that you need to describe at the scale of 1 by 1 kilometer the land use, because it's different. I mean, if there is a green area, you need to consider it. You cannot assume that everywhere, everything is paved. Also because this model allows you to make an assessment of the effect of urban greening, for instance. So if you put a patch in some locations, you put parks, you put green roofs, you need a detailed description at the scale of a green roof, or not much closer than that, which means that you have also to get information on the land use at such scale. So it's not easy. Another thing that I want to remind you here, we already mentioned them, but it's greenhouse gases, and it's not only CO2, I said. We also have methane, nitrous oxides like N2O, and halocarbons, as well as aerosols that are emitted when burning fossil fuels. So all of these gases, the information on the concentration of these gases need to be made available at the scale of the grid. Again, we can assume we are talking about concentrations in air. We can assume that they are not much varying in space. But of course, rigorously speaking, we should have this information available at the scale of the model. This is much interesting, and let me check in the web page because there are more pictures. I wanted to give you an overview of emission scenarios. So let's look at this one. So, okay. So what is this graph representing? These are future scenarios of human-induced CO2 emissions. And you see that up to 2020, there is only one straight line in black, which is the observed, estimated, not observed, estimated progress of emission scenarios of CO2 emissions. And then we have predictions for the future. These predictions are derived by socioeconomic models. These are models that are not based on conservation laws, by the way. These are different approaches. They use different equations. And they make a prediction of socioeconomic development and related emissions, CO2 emissions. In different configurations, there is the business as usual. The business as usual is the red line, is the more pessimistic, the red thick line. It's the more pessimistic scenario. It's called SSP 5.0.5, and SSP is the last generation of scenarios. And 0.5 is the identifier of business as usual. It means that we don't take any action to reduce human emissions. This is unrealistic because some actions were already taken. And you see that there are two red lines because there has been an evolution of SSP with respect to the previous generation of business as usual, deriving from a different socioeconomic model, a previous model, which is identified by the acronym RCP. 8.5 is unchanged, it means business as usual. But you see that the recent models give a more pessimistic evaluation. Now, there is the yellow line, which is SSP 4.6, SSP 4.6.0. And the yellow line is an estimate of the emissions with the current policies, the policies that were already activated. And this is the more realistic scenario, which foresees reaching a top of emissions around 2050, 2060. And this is more, let's say, it's different from the dashed line, the previous elaboration. It's more optimistic, I would say. Some scientists claimed recently that we already reached the top of the emissions, and now we are already moving towards decreasing them. Of course, the target of net zero by 2050, which is the target that is set by the European Union, is still doesn't look achievable with the current policies. On the other hand, the yellow line seems to be the more realistic one. And then we have different, more optimistic scenarios corresponding to target levels, different target levels. What are the target levels? They are the target that we want to meet by a certain date, or sorry, it's the target that we don't want to overpass in terms of global warming. So let me give an example. The target of the Paris Agreement in 2015 was max plus 1.5. We are already at 1.2. In 2015, we were around plus 1, and they fixed the target of max 1.5. It's the target that it's the temperature that we don't want. It's the level of warming that we don't want to overpass. There are other targets, plus 2, plus 2.5, because it seems that as of today, it seems that plus 1.5 is not easily reachable, and therefore people produced also the emissions that correspond to more, let's say, more realistic targets, and therefore you obtain these scenarios. Let me show you another graph, which is clearer. It's the same figure, but it's a bit clearer. Let me just go here and let me check where it is. I think it was here, actually. Let me just check. It's not here. Be patient a little bit. Okay, it's here. I don't understand why. Okay, I need to check if this graph is available to you. This is clearer. It's more or less the same numbers. It doesn't use the acronyms SSP, but you see no climate policies. And you see that it's an ensemble of predictions, because depending on the socioeconomic model that you consider, and depending on the initial conditions, you get an ensemble. And then there is current policies with the top at 2050, 2060. And then there is the target 2.4, the target 2, and the target 1.5. And you see that indeed the net zero corresponds to the target 1.5. It's clearly not achievable. And because net zero means that we can live without carbon, it looks like in 25 years, this is not to achieve. Because for energy production, for instance, it's not credible that we can reach net zero by 2050, because renewables will not be able in 25 years to cover all the increasing demands. Okay, so let me just check. Okay, I think we can stop here for today. Do you have any question? No questions. Okay, so see you next Monday, and time rushes. So at the end of the lecture of next Monday, we are already at half of the course, which is fine. We are in time, but still, if you have questions, don't wait too much. Thank you very much, and see you next Monday.